In this video, we're going to talk about the strength of acids and bases and how we actually quantify that. So far we've done some identifying of strong and weak acids. So we kind of have these, and bases. So we kind of have these two categories of strong and weak, but really it is a continuum. So within weak acids and weak bases, strength can differ. So we need to remember what strength really means. So in terms of acid and base strength, what we're really talking about when we say something is a stronger acid or base is that it has a higher percent ionization, that more of the particles, when they dissolve in solution, react with the water to form ions. So this is directly related to the percent ionization of the acid or base when it is put in water. So if something is pretty much 100% ionized in water, we call it strong. If something is a good bit less than 100% ionized in water, we call it weak. But there's a whole lot of territory in the less than 100 range. So things can be stronger or weaker within that category. So we express this idea of strength using an equilibrium constant, most commonly. So we specifically use the equilibrium constant for the reaction of the acid or base with water. So we talked a little bit about how acids and bases react with water in the first video. So for acids, we have what's known as Ka, or the equilibrium constant for an acid, that describes the reaction of an acid with water. So for a generic acid here, where A is some anion, when this reacts with water, water is going to function as a base and take the proton from the acid. So when our acid loses H+, all that's left behind is our anion. When water gains H+, it becomes hydronium. So the equilibrium constant for this reaction we call Ka, and the equilibrium expression is just the concentration of the conjugate base times the concentration of hydronium divided by the concentration of the acid. So water is a liquid, so remember that that gets left out. But this is what our Ka expression looks like for any acid. So you can plug in literally any anion and it's going to look the same. We're just plugging in that anion wherever we see an A. So one thing to note, when acids react with water, they only transfer one proton. Water can only take one at a time, one H3O plus. So if your acid has more than one acidic proton, if it is what we call a polyprotic acid, so poly for more than one, protic for protons or acidic hydrogens, So polyprotic acids have more than one acidic H, acidic hydrogen, but only one transfers at a time. Essentially, each acidic hydrogen has its own Ka value. So if we look at, for example, something like oxalic acid, which has two acidic hydrogens, when this reacts with water, we want to think about the protons transferring one at a time. So when we lose one acidic proton from this, we have one left. So we'll have HC2O4 minus and H3O plus. This reaction would have an equilibrium expression, and its equilibrium constant would be the first dissociation constant, or Ka1 is how it would sometimes be noted. This conjugate base still has an acidic hydrogen on it, so that can go on to react with a separate water molecule. To give us the oxalate ion and another mole of hydronium. So the conjugate base in this first reaction was the acid in the second reaction. So both of these are really happening, but we do want to think of them as separate reactions because they have separate equilibrium constants. So when we're reacting with water, and that's all, we want to think about losing the protons one step at a time. And this is different than when we wrote neutralization reactions where we just ripped them all off at once. In a neutralization reaction, you're reacting with a much stronger base than water. So even if you're reacting with a weak base, it's still much more basic than water by itself. So for this type of situation where we're just putting an acid in water, always just lose one proton at a time. So for bases, things are a little bit less complicated. Or really they're essentially the same, but for bases, we have Kb, which describes the reaction of a base with water. So if we have some generic base that we shall label B, and we put that in water, water is going to act as an acid here, which means that it's going to give a proton to the base. So when the base, which I had B minus, I had it as an anion initially, just as a generic representation. When that gains H plus, it's going to become HB. And when water loses H plus, that's going to become hydroxide. So our equilibrium constant for this type of equation is known as Kb. There's always a base plus water. And our equilibrium expression is always the concentration of the conjugate acid times the concentration of hydroxide over the concentration of the base. And again, the only thing that would really vary here is what is your base. So if we think about these expressions that we have for Kb, for bases, and Ka for an acid, they are products over reactants, and the products of these reactions are ions that we're forming hydronium and hydroxide in these two processes. So the more products we're forming, the more ionized we say that substance is, which means that our product concentrations would be larger, giving us a larger value for Ka or Kb when we have a more highly ionized substance. So more ionization means a stronger acid or base. So a larger value of Ka or Kb means that something is a stronger acid or base, respectively. So we can also use this idea to help us better identify weak bases. So this gives us another relationship between an acid and its conjugate base, and a base and its conjugate acid. So if we look back at the reactions we wrote here, we have an acid, it loses a proton to become its conjugate base, and we have water functioning as a base, gaining a proton to become its conjugate acid. And same type of relationship in the base equation. We've got our base gaining a proton to become its conjugate acid, which means that water is functioning as an acid. And when it loses a proton, it becomes hydroxide, which is its conjugate base. So the relationship between base and conjugate acid, or acid and conjugate base, between a conjugate acid-base pair tells us something about the strength of those two things. So essentially what it boils down to is that we said that weak bases were kind of the weird ones to try and identify because they can be a lot of different things. There are no real structural similarities, but what is similar is that many weak bases are anions, are negatively charged, and an anion that is the conjugate base of a weak acid is a weak base. So we know that most acids are weak acids. We have a very short list of strong acids, and any anion, if you attach hydrogen to it, can be an acid. So we have a lot of weak acids in the world, which means that most anions function as weak bases, and there are only a few that don't, and those are the conjugate bases of the strong acids. So the conjugate base of a strong acid is not a base at all, is not a base at all. We'll leave it at that. So essentially that would likely be in the none of the above category. It is not capable of functioning as a base. One to be aware of is the conjugate base of sulfuric acid, which is H2SO4. When it loses one proton, still has an acidic hydrogen, so it's not a base, but it is still an acid. So we see that the conjugate base of a weak acid is a weak base. The conjugate base of a strong acid is not a base at all. So what we really have here is an inverse relationship between the strength of the things in an acid-base pair here, that the stronger an acid, the weaker its conjugate base. By the time you get into strong acid territory, it is too weak to function as a base at all. So for a conjugate pair, for a conjugate acid-base pair, the Ka for the acid times the Kb for the base is always constant at constant temperature, is actually equal to Kw. If you work out the equilibrium expressions, you can actually prove this to yourself. I'm not going to do it now just for the sake of time, but we can see from this relationship that if the product of these two things has to be constant, as one increases, the other has to decrease. So if Ka is larger for a particular acid, Kb must be smaller, meaning that because the acid is stronger, the base has to be weaker. So we can use this to help us predict relative strengths of things, that even if we have a bunch of weak acids, we can use their Ka values, which are easily looked up in a table, to figure out which is the strongest acid or the weakest acid. And even just knowing the Kas, we can figure out something about the strength of the conjugate bases as well. So for example, there we go. Too far away. If we have these three acids as examples with their Ka values, we can determine which is the strongest acid of those three acids and which is the strongest base of their conjugate bases, just from the information given. So why don't you pause here and try to do that on your own based on what we've discussed so far. So what we should see here is that this first acid, HClO2, has the largest value for Ka, which means it is the strongest acid. So the strongest acid of the ones listed is HClO2, since it has the largest Ka. So that is really straightforward. Which is the strongest base? We have to think one step further. So the strongest base is going to be the conjugate base of the weakest acid, since we have an inverse relationship between the acid and conjugate base strength. So the weakest acid is going to be the one with the smallest Ka, so smallest Ka, weakest acid. Weakest acid means it's going to have the strongest conjugate base. So the conjugate base of HBRO is BRO minus, so that would be the strongest base of the options listed.